What's up, bitches? Today we're going to learn Brayton cycle with regeneration, okay? What you see on the screen is a simple Brayton cycle, okay? You have your compressor, goes into the combustion, then turbine, heat exchange, and that's your TS diagram over here. Wait, let me move it. That's your TS diagram, okay? For the regeneration, you literally just have one extra step and that's it, okay? So I'm just going to remove this. So after the turbine, some of your heat is going to go into what is called a regeneration thing. Okay? And basically some of the heat is going to be used to reheat the compressed air. Why are you going to do this? They basically just do this to increase the thermal efficiency. And then you're going to have this box and then the outlet. And in the regeneration cycle, you don't have a heat exchanger at the bottom over here. You just have your inlet. Whoops. Whoa. You don't have this part. You just have your inlet. Now, there's a good chance that in your notebook, it's going to be written differently, but this is the basic concept. For the sake of the TS diagram to be more simpler, they name this part the fourth part. Over here is step 5, and over here step 6. So it's not going to be exactly in order, but they just use this because they're taking the simple Brayton cycle as a reference, okay? That's why. So if you don't really understand this, you don't need to know this part by heart, but you really need to understand the TS diagram. So I'm going to explain to you guys exactly what happens, what is going on here. So for the regeneration cycle, you're going to consider these lines over here, because some of the turbine heat is going to be used. In all of your problems, you're going to have a regeneration efficiency over here. If it is at 100%, you're going to have step 6. That's exactly the same temperature as step 2, and all of that heat is going to go back. Okay, that's it. This is if it's at 100%. If it's not at 100%, it's going to look something like this. Let me erase it a little bit. It's going to be like somewhere around here, and it's going to go somewhere around over here. Okay, that's it. So basically, the way you solve your problems for all of these is that you have to consider that it's at 100. If it was at 100%, whoops. I don't know, it's a little bit hard to explain, but basically, this part over here is your Q region. Okay? Q, which is the heat that's being regenerated, is equal to Cp times. If this was at 100% efficiency, it would just be equal to T4 negative T2, which is over here from here. So you just take that into reference, and then you multiply it by the regeneration efficiency. That's it. This is the only the only formula that's being added, okay? For this Brayton cycle. For your Qin, it's not exactly like the simple Brayton cycle. Your Qin is literally this part. Okay? Because the rest, you're assuming that the rest is being added by the fifth step, okay? So Qin is basically Cp T3 negative T5, okay? But you don't need to use this. You're going to have to use Cp. And you're going to take this entire part over here from T3 to T2, just like if it was in the simple Brayton cycle. And then you subtract the Q region. Okay? This is the formula you want to use for Q in. And it's the same thing for Q out. Your Q out is only this part over here. So Q out equals to Cp. You take the entire thing, T4 negative T1, just like as if it was a simple Brayton cycle, and then you subtract the Q region. Okay. These three equations, you really have to know them. That's what really separates the simple Brayton cycle compared to the regeneration. And for your exams, you have to know this TS diagram by heart. So if you have a formula sheet, you should write these three equations over here and the TS diagram. So that's it. And most of your questions, they're going to ask the thermal efficiency, which the easiest formula to use is 1 minus Q out divided by Q in. All right. So now let's do an example to practice. All right. So this is the problem that we're going to use. I'm not going to read everything, but I'm just going to explain to you guys step by step and use this as an example. Okay. Whatever is important, I highlighted. So the first thing that you do when you get your questions without even reading the question is you draw your TS diagram. Okay. We're going to draw the simple Brayton cycle. 2. Over here, 3. Then it's going to look something like this. 4. That's it. This is your simple Brayton cycle. Okay. Make sure that 0.4 is like above the temperature at 0.4 is above temperature at 0.2. So now we can read the question. It's giving us the pressure ratio, which is just a fancy way of saying P1 over P2 equals 7. You have your minimum and maximum temperature, and then we have our efficiencies. So we have this shit equals to 0.75. We have this shit equals to 0.82. What do these mean? Basically, it means that it's not going to be like this. This is ideally. If you have the compressor, if your compressor efficiency isn't at 100%, it means you're going to gain some temperature. It's going to go up like this. 2. Same thing with the turbine. It's going to be over here. 4. This point is for ideally if it was at 100% efficiency. Then it's giving us the regenerator effectiveness. This 0.65. So we're going to take step 4, draw this line, then step 2 and draw this line. Okay. These, if this, well, somewhere over here is going to be step 6, but these would be connected if it was at 100% efficiency. But since it's not, it's going to be a random point over here. It's not really important. I'm going to draw over here and it's going to go somewhere over here. The exact values aren't important. You don't need to know the temperature at T5 and T6. You just need to know the temperature at T1, 2, 3, 4. Okay. So you have P1, T1, P2, T2, P3, T3, P4, T4. All right. Now we can start answering the question. It's asking us the thermal efficiency. So thermal efficiency is equal to 1 over Q out negative Q in. We know that Q in is this point over here, Q in, and Q out is over here. So we have to find T1, 2, 3, and 4. And the rest is super easy, okay? So, whoops. Hold on, give me a second. All right. So, keep in mind, just like, well, I'm assuming that you guys learned the simple Brayton cycle, but from point 1 to 2, it's isentropic. Same thing with over here, it's isentropic. Damn, bro, this diagram's ugly, but whatever. T2 over T1 equals to P2 over P1 to the power of K minus 1 over K. So T2 equals to T1 times our pressure ratio, 7. And since it's air, we're just going to assume it's ideal gas. It's equal to 1.4. So to the power of 0.4 over 1.4. Okay. T1, we're going to set this at, what did it say? 310K. Okay. So, oh yeah, I forgot to explain. The minimum temperature is, you're just going to look at the point where it's like the lowest on the y-axis, on the t-axis over here. So 310K. And the maximum temperature is over here at the top. So 150. Okay. So all that's left is to find T2 and T4. Super easy, okay? This, if you calculate this, we find the ideal temperature if the compressor was at 100%. It's going to be equal to about 540.53. Ideally. Okay? Since we have a certain efficiency, we have to use this formula. Divided by T2 negative T1. Since it's going up, you're going from 0.1 to 0.2. The thermal efficiency, you're going to use the ideal as the numerator, okay? We have all of these numbers. We're just looking for this, okay? So I'm not going to write it out, okay? I'm just going to, like, this is just simple basic algebra, okay? But you're supposed to find T2 to be about 607 Kelvin. 617. 17 Kelvin. If you get something lower than T1, that means you fucked up with these numerators over here. Okay? Just keep in mind that the ideal, since it's not 100% efficiency, you're going to gain some heat. So the actual T2 has to be more than the ideal T2. Okay? This is just in case if you fuck up the numerators. Next, let's find T4 equals P4 negative P3 K negative 1 over K negative. Since we're going down, I put negative. So T4 equals to T3 150 times the pressure ratio to the power of negative 0.4 over 1.4. This should give you, ideally, a temperature of about 659.54 Kelvin, ideally. You do the same shit as we did for the compressor. You have your temperature, turbine, 0.65. T3 negative T4. T3 negative T4. Since T3 is higher than T4, I don't want to have a negative value. That's why I did T3 negative T4. Since we're going down this time and we're gaining some heat, your ideal T4 is going to be at the denominator over here. Okay? So we have this value, this over here. We have T3. We're looking for this. So you just do basic algebra and you're supposed to find the actual T4 to be about 748 Kelvin. All right. We're almost done. We have all the values we need, okay? Now, we need to find Q regen. It's equal to Cp times T4 negative T2. This is if it was at 100% efficiency, but since we have an efficiency for the regenerator, we have to take that into consideration. So Cp for perfect air is 1.004 times T4, 748, negative T2, 617, times the efficiency, which is 0.65. This is going to give us a value of about wait, no. Sorry. It's going to give us a value of about 85.5 kilojoules over kilogram. We have our Q regen. Now, Q out is this bottom part over here. It's going to be equal to Cp T4 T1. This is as if it was a simple Brayton problem, but we have to take into consideration whatever is being used in the system to regenerate. So 1.004. T4 is what we found, 748. Negative T1, 310. Negative our Q regen, 85.5. That's going to give us a value of about 354.25. Same thing with Q in, Cp, T3 negative T2. This is as if it was a simple Brayton problem, but we have to take into consider the regeneration. 1.004, 1150 minus 617 minus 85.5. That's going to give us a value of about 449.6. That's it. And the thermal efficiency is equal to 1 minus Q out divided by Q in equals to 1 minus 354.25 divided by 449.6. That's going to give us a value of about 21.6%. So Just keep in mind that you really don't need to find the temperature at 0.5 and 6. You just need the temperature T1, 2, 3, 4. And the rest, you just have to follow the formulas. And that's it. That is exactly how to pass. Thank you for watching. Subscribe.